We are talking today about rotational mechanics still. We are going to be looking today at torque. All right? Now, before we can talk about torque, however, we need to talk about moment of inertia. In other words, what the heck is a moment of inertia? What is inertia? And how does it affect rotation? So what is it in linear motion? Thank you. That's the basic, that's what it comes, or object at rest stays at rest. Yeah, it's Newton's laws, isn't it? Sort of. What it means is something wants to resist what? Movement. Resist change. It's like all of us. We are victims of inertia. We don't want to change. Okay, so in linear motion, inertia is resistance to changes in motion. From forces. This is important, from forces. In other words, what changes here? If we are applying a force, we're talking about what? Mass and acceleration, so it's based on mass, isn't it? Okay, now in rotational motion, it's not just about mass.
I'm guessing we finished this packet last class. The guided notes.
Yeah, we did. It's recorded and online.
Okay, got it.
Rotational motion. It is both mass and the shape. In other words, in rotational motion, inertia is resistance to what? It's resistance to rotation due to force. But here's the thing. Depending on where you apply that force to a rotational object, whether you apply it closer in or further out, that also has an effect on how much force you have to use. I want you to think about it. I'm going to carry this with me because I'm recording. I want you to think about it, and let's talk about this right here, this door. Why is the doorknob way out here? Makes it easier to push, doesn't it? Any of you ever tried pushing a door here versus, I want you to see something. I just have to barely push to move it here, don't I? However, to get it to move that same amount, I have to push harder. It feels harder. The closer I get to the edge here of this hinge, the harder I have to push to get it to move the same amount. So it's not just how much force I'm doing. That force is dependent on how close to the pivot it is, or the center of rotation if it's a mass like a pulley or something. So it is a product of both mass and shape. Okay? Now, in general, the further away the mass is from the center, the harder it is to get it to change. I want you to think about why that is. If all the mass is spread out from the center and you grab the edge, you're not grabbing nearly as much mass at one time, are you? So I want you to think about, would you rather have a big spinning plate and have to stop it by grabbing the edge? Or would you rather have a big spinning ring, the same mass, but it's a hollow ring, and have to grab it at the edge, which is where all the mass is, and move it? You'd rather have the disc, because some of the mass is in here closer, some of the mass is further away. You're going to want to be changing it. You want the mass to be more distributed, okay? more distribution of the mass, the wider it is, the more it's distributed closer to the axis, the easier it's going to be to change the motion. But if all the mass is out here, you're having to grab all of it at once and try to stop it, aren't you? If it's all spread out, you're only having to grab some of it. I'm not talking about the door anymore. I'm not talking about taking less force to move it here versus here in the middle. That's torque. We're talking about the actual moment of inertia. Once it's in motion, it's harder to move something if it's further away from the center of rotation. I won't say to rotate, the harder it is to change, okay? So I want you to think about that. A hollow sphere would be easier to would be harder to rotate, excuse me. It'll be harder to change the rotation than a solid sphere. So if it's just sitting there and you had a hollow sphere and a solid sphere, you'd rather have the solid one to turn. If they're the same mass. Now, if they're not the same mass, that's a whole different ball game.
Right.
But if they're the same mass, hollow is going to be harder to get to move than solid is.
We did this with like tape and a ball.
What you guys did, what we did was we looked at the rate of rotation for something, a solid disc and a hollow disc.
Yeah.
Yeah. Which one hits the ground? Which one goes to the bottom first? The one that had more inertia, which is what we're talking about, more rotational inertia, had less translational, right? So the one that had all the mass out here actually got to the bottom after the one that was solid. Okay? So what is it for a point mass? What is inertia? Inertia is big I. For a point mass, I is equal to mr squared. So what are the units?
Kilogram meter squared.
Yeah, kilogram meters squared. So I want you to think about how this explains what happens when we have something rotate, when we have inertia. Grab what I need. Grab it during takeoff. Good thing I live by my phone. You guys have done this before. He hasn't seen it. Sam hasn't seen it. This is very easy to rotate. Very easy to rotate, okay? Now, if you get on this guy, Lord have mercy. Goodness knows it doesn't make you probably need to. I'll do it anyway. If we get on this, and I start with my arms out, rotating, and I pull them, what happens?
Spit out.
I spit out. Okay. Now, that's the ice skater phenomenon. Have you ever watched a professional ice skater? When they spin, they bring their arms in, don't they? Or when they do jumps like triple axels or quads, they're bringing themselves in as close as they can, aren't they? And then what do as they're coming out? Their arms come out. Slow themselves down. Slow the rotation down. That is a product of this idea of rotational inertia. What they're doing when they bring their arms in is they are pulling their mass in closer. If they pull their mass in closer, it's easy for them to. Whereas if they bring it out, they're putting more mass further away, which makes them more resistant to rotation. Okay, so they're slowing themselves down. It's in and out, okay? It's that mr squared right there. It is the matter of them, their mass didn't change, so what changed was their radius squared. And as you can see, it makes a big difference, doesn't it? So, yeah, they're doing them all over the place now. I watched the Olympic competition, or a national competition a couple weeks ago where this guy is known for it. He did like 5 or 6 different quad jumps in his long skate. It was crazy how many he did. He did so many and was so good at it that he missed one and actually fell and still blew everybody else in the competition away points-wise. I mean, by far. I mean, how good do you have to be able to fall in the middle of your long program and still decimate the competition? All right, so let's read this. Example A, an Olympic skater is spinning and pulls her arms in to speed up her spin. Explain how that is possible. So pulling her arms in does what? Yep. Reduces her radius. Which what? It reduces the inertia. So it increases her angular acceleration. It's not actually her speed that goes up, it's her acceleration that goes up, which by then also increases her speed, doesn't it? So how do we calculate the moment of inertia when something is a nice, wonderful object? It's nice and symmetric, and it's about its center of rotation. You can see the picture. You've got a bar. The axis of rotation is through the center, right? Through the center of mass. So there's 2 different things we need to look at here. We're going to look at inertia from both cases. We're going to look at it in terms of through the center of mass rotation, and we're going to look at it what happens when it's not in the center of mass. What happens when the pivot is not at the center of mass? It's a very different calculation, okay? So if it is through the center of mass, what you get is this. I equals the integral of r squared dm. In other words, we're going to treat it as a bunch of small particles, just like this. We've got a bunch of small particles, and we are going to what? Integrate from zero to r. Okay? Or from 0 to m, really, if you think about it, because it's dm, not from 0 to r. It's from 0 to m. All right. Now, because for a point mass, of course, it's just mr squared. For a system of masses, it's the integral. Units for moments of inertia, of course, again, is kgm squared. Now, let's actually do this. Let's actually find the moment of inertia for a rod with an axis perpendicular to the rod. That's this guy right here. All right? Distance from the end of the rod to the pivot. So we're going to say the pivot is here, all right, where y is. And we're, of course, going to break it into a bunch of little slices, right? These slices are all dm. But we also know these are lambda dx, right? Because it's just along its length. The distance from the end of the rod to the pivot is a. Okay? And the entire length of the rod is L. Is everybody seeing that? We take our little slices, we make our little slice. All right, so now what? Now we got to do our actual, you got to figure out where this is. The center, X and Y, is here. So this end is at negative A, isn't it? And this end is at L minus A. Do you agree? Does everybody know where that came from? This is the y-axis, this is the x-axis, so this is 0. So we're going back A, the whole thing is L, so it's L minus A at the other end. Our distance from here to here is some x value, so that's our R. Integration. So let's do our, whoa. Yeah, here we go, whoa. Let's do our integration here. So what we're going to get is, we know what? Inertia is equal to the integral of what? R squared dm, right? Let's start with that. Integral of R squared dm. Well, R squared dm, we're doing x, aren't we? We are integrating from where? If you look at this guy, you've got A. Look back. These are our limits of integration, guys. We're going from negative A to L minus A. All right? So now what? We're going along the x. Our distance is x, isn't it? The distance to our whatever. So we're doing, instead of R squared, we've got x squared dm. Well, we know what dm is, don't we? Didn't we find that? It is the linear density times the dx, right? The little slice, the width. Yep. So this becomes negative A, from negative A to L minus A, x squared lambda dx. That's not so bad, is it? Well, lambda is linear density, isn't it? So that would be mass over length, right? So let's put that in. So I is from negative A to L minus A, m over L times x squared dx. We could move this to the outside, couldn't we? Because it's, how much integration have y'all done so far? Much? Any?
Not a lot.
If it's a constant, you can move it outside the integral. Okay? That's what the m over L is going to do. So now I've got the m over L integral from negative A to L minus A of x squared dx, which we can now integrate. So let's do that. X squared becomes what? X cubed over 3. And we're going from negative A to L minus A. Okay? So that is going to be m over L times the entirety. This whole thing is the inertia. First condition minus the second condition, right? So it is going to be L minus A cubed over 3 minus negative A cubed over 3. So we can clean this guy up. Let's see that the inertia is m over L. L minus A cubed plus, and this whole thing is cubed, plus a cubed, because minus a negative becomes a positive, doesn't it? All over 3. I could continue to clean this up some. Do you know how to do a cubic?
No.
Oh, come on. Y'all ought to be able to do a cubic in your head. This would be L cubed, what? Minus 3L squared A. No. Yeah. Plus 3LA squared minus a cubed, then plus a cubed, all over 3. So this goes away. We can pull an L out of all of them, can't we? You see that? So we can pull an L out here, we can pull an L out here, this can become a squared, and it goes away with that. So we get M over 3 times what? L squared minus 3LA plus 3A squared. That's your inertia. Now, that's if it's not at the center. Now, what if it's at the end? What does it look like? Is it going to be the same? The inertia is not going to be the same, is it? If it's at one end, should the inertia be higher or lower? Should be higher, because you've got more mass further away from the pivot, don't you? What about if it's in the center? You've got less on each side, but you've got more on. If it's not exactly in the center like the first case, no. So if the rod is at the end, it becomes this. Inertia equals M over 3, which we said. L squared. Well, A becomes 0, doesn't it? So this whole expression right here, this goes to 0. Think about it. That ends up going to 0, and that ends up going to 0, doesn't it? Alpha, or A, is 0, so it ends up being 1/3 mL squared. So now what if it's at the center? How does that change? We've got inertia figured out, don't we? For anywhere? Still M over 3. It's not L, it's still L squared, isn't it? Minus 3L times A plus 3 is squared. See, the total length is still L in all of them. A is what changes. Does everybody understand why A is now L over 2 versus A is 0 here? We're putting the pivot at a particular place. All right, so now what does this become? We got L squared minus 3L squared over 2 plus 3L squared over 2. They don't cancel out because the 2 is squared here, isn't it? So we have 3L squared over 4. So we have 1 plus 0.75 minus 1.5. In other words, we have M over 3. We have L squared minus 3/2 L squared plus 3/4 L squared, and then over 3. So this is 1/4 L squared, isn't it? Times m over 3 makes it 1/12 m L squared. So if we put the rod privet at the center, it is much less inertia, isn't it? Yeah, it's 1/4 as much. So now, let's look at a cylinder with an axis through the center. We're still going to start the same every time. Integral of r squared dm. Now, if we have a cylinder, it looks like this in cross section, doesn't it? This is radius 1, and then we have radius 2. Do you agree? It's like a cylinder's got a thick wall with an empty center. Okay, so this ought to have fairly high inertia compared to what we just looked at. But this is now what? We're now talking about a volume. So now we got to look at dm for a volume, which is yes. So what is dV? Area of the base times the height, right? So we have what? dV is d of the volume, which is pi r squared, times the length, whatever the length is, right, or the height. And we're going to say L is the length of the cylinder, right? So this would be the derivative of that. So it would be 2 pi r dl. Or 2 pi r, no. Nope, because L's not going to change. It's just a constant. 2 pi r L dr. Right? Really should say big dr. Because r is what's changing, isn't it? The size of the radius. So now let's start plugging stuff in here. So we have I equals this guy. From where to where? What are my limits of integration? What are we integrating, guys? This outside edge, aren't we? So from the innermost edge to the outermost edge. What is the innermost edge? R sub 1 all the way to R sub 2. That's what we're integrating. Of R squared dm. Well, we know what dm is, don't we? dm we just found was rho dv, correct? And dv we found was this. So this is going to be what? R squared, and then all this mess right here, rho times 2 pi RL dr. Whee! Now the nice thing is that the whole bunch of that is constant, isn't it? So let's pull out everything that's a constant. Rho is a constant. 2 is, pi is, L is. So from R sub 1, uh-oh, that's not good. here we go. From r sub 1 to r sub 2, really all we're doing is what? R cubed dr. So what is the integral of r cubed dr? Yeah. From r sub 1 to r sub 2. I do need to tell you that really you don't have to memorize any of these. If they want you to use them on the test, they'll give them to you or they'll make you integrate it. The one you need to know is mr squared. The integral of r squared dm, basically, or mr squared. So can we finish this one? We got to replace rho at some point. We don't know rho, we don't know L. So it'd be nice if we could replace those, couldn't we? So what is rho? Rho is equal to what? M over V? Well, M is M. V is this area, which is going to be a difference because you've got a ring. It's not a full circle, is it? It's the area of the outer circle minus the area of the innermost circle, isn't it? Yeah. This is not a really nice one, is it? The further you get in Physics C, the messier stuff gets. So 2 times m over the volume, which is going to be pi L. And we have r sub 2 squared minus r sub 1 squared. Which is kind of nice because now we have times pi times L, and the L's are going to go away, the pi's are going to go away. Yay us. And r the fourth over 4 from r sub 1 to r sub 2. And now 2 goes into 4 twice, right? So what we have is 1/2, or m over 2, over r sub 2 squared minus r sub 1 squared. And then we're going to do this guy up at the top. We have r to the 4th. We have r sub 2 to the 4th power minus r sub 1 to the 4th power. Now, y'all gonna hate me for this one. R sub 2 to the 4th minus r sub 1 to the 4th is the difference of 2 squares. Isn't it? Why am I even bothering with that? Because what?
Lead us through and show us.
Well, I would kind of hope that you would see that. What is the difference of 2 squared? A squared minus b squared is what? A minus b times a plus b. So, if you see where I'm going with this, the inertia now is m over 2, r sub 2 squared minus r sub 1 squared times r sub 2 squared plus r sub 1 squared, all over this right here became this. And now look what happens. That goes away. So this becomes 1/2 m times r sub 2 squared plus r sub 1 squared. Now let's actually get to using some of this. Sure. I know. I get in integrals and you guys, I just see the fear response and you shut down. Just try to roll with it. It's higher level math. It's the calculus. Now, for the most part, you're not going to have to probably do this. They're going to give you the inertia. But part of it's my job to kind of show you where it all develops from. Now, parallel axis theorem, they're going to make you do, but that's easier than this. It doesn't require integrations. All right. Moment of inertia, point masses. One object on another object about the center. You got three objects here. When we looked at this in Physics 1, we never had the object in the middle. We just had point masses that were connected by a massless bar or string or something. This bar has a mass, okay? It's like a dumbbell, isn't it? Like you see? All right, so we have three objects. It is pivoted about its center. So we need to know where the center is. It's going to be pivoted about here, isn't it? So this is my rotation. So I need to know what length everything is at. Now the really cool thing is that guess what? Do you remember how we find the center of mass? It's the distance from the center of pivot to the mass. We'll look at it. If that bar in the middle is symmetrical, then we are at the center of mass for the bar, aren't we? So the distance to it is 0. So it kind of goes out of the equation, so to speak. Okay? You got three objects for sure. You've got a rod of length L and a mass M pivoted about its center. We know what that is. We know its inertia. We just found it. It is 1/12 mL squared, isn't it? That's that mass, correct? Didn't we just find that a minute ago for the bar? Now we have a sphere. We have, that's a point mass, so that is mr squared, isn't it? So that is m, r is L over 2 squared. So this is 1/4 mL squared. They can both be treated as point masses. And there are, how many of them? 2. So the total inertia, I total, is equal to the inertia of the bar plus twice the inertia of a sphere. Inertia of the bar we found was 1/12 mL squared. And this we found was 1/4 mL squared. So we have 1/12 mL squared plus 1/2 mL squared, which is what? 6/12? So this becomes 6 over 12. So this ends up as 7 over 12 mL squared. And that's the total inertia for that system. Okay?
But the mass of the bar and the mass of the sphere is just the same. Right?
Oh, yeah, it should be little m. Excuse me. What did I do? I put a big M, didn't I? Here, little m, and then I can't do that, can I? Okay, so never mind. Thank you for catching that. It's been a long day. Okay? So now, parallel axis theorem. If something is not pivoted about its center of mass, notice in this picture the center of mass is here, right? So here's the center of mass, but the pivot is over here. So how do we do this? Well, there's a formula. The inertia at the pivot, I sub p, is the inertia at the center of mass plus md squared. Do you want to know what d is? It's the distance of the pivot from the actual center of mass. Makes sense if you think about it.
What was the word read on this? I just couldn't see the last.
This is
Over 12?
big M, yeah.
Okay.
And this is little m. Two different masses. Okay? This should be little m. So I sub p is the moment of inertia. About an axis parallel, no way, it's called the parallel axis theorem now, to the center. I sub cm is the moment of inertia about the center of mass. M is the mass, of course. D is the distance from the axis of rotation to the center mass. And guess what? I sub p is always greater than I sub m. Think about it. The least center of mass something's always going to have, or the least inertia something's always going to have, is if it is rotating about its center of mass. Does that make sense to everybody? That's the least it's ever going to have. Okay? So let's look at an example here that's not going to be so hideous. This is more along the lines of what you'll have to do, especially with, they love parallel axis theorem problems too. Know your parallel axis theorem, okay? It is not on your, I don't think it's on your formula sheet. It might be. I don't think it is. Consider a solid cylinder of radius r and mass m. Yeah, check it. Is the parallel axis theorem on your formula sheet? Huh? You don't see it? Well then, it's one of the things you need to know. Circle it, put a star next to it, make it a happy thing. So you've got a solid cylinder of radius r and a mass m. Find the moment of inertia of a solid cylinder of radius r and mass m about its center and versus an axis tangent to the center. So the first thing we want to do is find it if we're rotating it about its center. Okay? So we know this is R. So a solid cylinder, we know what it is for a cylinder, don't we? I is m over 2 r sub 1 squared plus r sub 2 squared. Guys, we just found this earlier, didn't we? Well, r sub 1 is 0 because it's at the very center, and r sub 2 is r. So this basically goes away, doesn't it? So this is 1/2 mr squared. So for a cylinder, the inertia is 1/2 mr squared. Now what about an axis tangent to the cylinder at its outer edge? So now we want it to rotate about this guy over here. Okay? So how far is it from here to here? R. It is some distance, the distance R. So this is where we have to use our parallel axis theorem. So we're going to use I sub p equals I center of mass plus md squared. Well, we know the center of mass normally. We know what the inertia is. We just found it. It's 1/2 what? mr squared. The mass is still m, isn't it? Well, how far is it from the axis to the of rotation to the center of mass? R, isn't it? So we've got 1/2 mr squared plus mr squared. is going to be what?
3
3
halves.
halves mr squared. That is the inertia for if you move, just moving the axis of rotation from the center of the object to the outer edge of the object tripled, if you think about it, tripled the amount of inertia this thing had. That's like saying if I take something and I spin it about its center, something round, if I spin it about its center, it has a certain amount of inertia. But if I take it here and I have to swing it around and spin it 3 times more, because there's just that much more inertia, and there's just that much more mass having to be swung. Here, we're only ever having to swing half of it around, aren't we? Literally half. Do you understand why it's 1/2 mr squared? You're literally only having to swing half the can around the center. However, if we come out here, this is the whole can. So you'd think it'd be double. It's not double. It's triple, because it's that much harder, because not only have we doubled the mass, but we've increased the distance away from the pivot that total mass is, haven't we? So it's 3 times. Makes sense if you think about it from that standpoint. What do we think about this? Kind of, sort of, not 100% sure about it. Your brain is smoking. All right. I feel like if I jump into torque, it's going to get ugly. And Addie's not here anyway, so why don't we stop at 5.2, moment of inertia. That's probably enough. You're like, uh-huh, it is. And you guys can get started on your 5.2 exercises, okay? So you need to do 5.2 exercises in the thing. Now, if you want some additional practice, you can do the 5.1 as well for rotational stuff, but you don't have to. Just do the 5.2.